everything. So, good afternoon. Welcome to this first NISQ webinar, the first one of a series of 9 between now and February 2022. I am Pascal Bernier-Bruna. I'm the communication leader for the NISQ project, and I will be your host today. This webinar is recorded, and you will receive the link to the recording on Monday. It's in listen-only mode because we have a lot of people registered. I don't know if everybody will attend, but that's a lot. So so we're in listen-only mode, but you can use the Zoom Q&A panel to ask questions to the speakers, and you will be able to see the questions asked by others. You will be able to upvote questions, comment on them, and the chat is also open for more informal exchanges. Before I hand over to today's speakers, I would like to introduce the NISQ research project and our use cases and explain why we are presenting this today. NISQ stands for Next Applications of Quantum Computing. It's a 4-year project that started in September 2020. It's a project funded by the European Commission's Horizon 2020 program. We are part of the Quantum Technology Flagship. And we are a multidisciplinary consortium of 12 companies and research labs. You can see our logos here. Our objective is to boost practical applications of quantum computing in the NISQ era. And we are a use case centric project. All use cases are endorsed by an industrial partner and investigated by an integrated team of industrial and academic partners together. Also, each use case is committed to develop open source NISQ programming libraries. So our use cases cover 3 domains, 3 main areas. The first one is chemistry with CO2 recapture and drug discovery. And if you have an interest in quantum computing for chemistry, we have a workshop at EQTC about this. That's on the 1st of December. The second area is machine learning and optimization, and that's where we are today, if I can say. We have 4 use cases in this domain: reinforcement learning for stock management, hard optimization problems for energy management, financial applications, and HPC mesh segmentation. And the last domain is symbolic AI and graph algorithmics with 3 use cases: quantum natural language processing, quantum probabilistic safety assessments, and quantum rule-based systems for breast cancer detection. And what I would like to stress is that the project as a whole is committed to build a community with potential users of industrial NISQ applications. And that's why we are organizing this webinar, because we want to share knowledge and exchange beyond the project partners with other potential users. So let's get on with today's agenda. And first, I would like to introduce Dr. Vedran Dunjko from Leiden University, who will moderate the Q&A and discussion today. In our project, he's the work package leader for this machine learning and optimization group of use cases. And I mean, he deserves big thanks because he's not just the moderator, he organized this webinar and the other 3 November webinars. So Vedran, could you explain how you built this agenda?
Thank you very much, Pascal, for this kind introduction. And I hope you can all clearly hear me. So as you explained, the basic idea behind our project is to pair up a particular case study, which has been for years investigated by our industrial partners and their experts, with an expert in quantum computing, to simply identify ways to mix and match technologies with problems. But as we all know, quantum computing is a very special type of a hammer, right? And we all, as Aronson says, and we're all looking for the right nails, and technology changes very quickly, and our understanding what quantum computers could be used for changes very, very rapidly, and specifically with the developments in actual quantum devices. So the idea behind these seminars is to invite an external expert in quantum computing without necessarily worrying too much of whether their particular research is tailored to the types of problems we care about. We are interested in all those possibilities which we might miss if we simply focus too much on the most obvious connections. So it is my great pleasure to host today Maria Schuld and Reda Alami. Maria Schuld is one of the certainly best recognizable faces in modern day quantum machine learning. She's one of the pioneers in quantum machine learning, which was tailored and directed toward near-term quantum computers. She did her PhD in the University of KwaZulu-Natal in South Africa and did her first postdoc there. And now she's a senior researcher at the startup company Xanadu, which is developing both quantum machines and quantum software. And she's also a part-time researcher at the University of KwaZulu-Natal. And as I mentioned, she's one of the really founders of modern day approaches to quantum machine learning. And I'm really excited to hear her reports and what's been happening in the field. At the same time, from the side of the NISQ project, we have Reda Alami, who is now a researcher in TotalEnergies. He's an expert in reinforcement learning techniques and also problems dealing with uncertainty. He did his PhD in a joint doctoral program between Orange Labs, Paris-Saclay University, and India. And he will be talking about one of the more important problems that the industry is facing nowadays in his sector and classical solutions to this problem. So they will be presenting their talks. Maria will have 40 minutes, followed by 5 minutes or so for very technical questions about her particular topic, followed by a 20-minute presentation by Reda focusing on the particular use case we're interested in. And in the end, we will have plenty of time for a discussion and question session where we will invite everybody to phrase their questions to our invited speakers. But also we will ask Maria and Reda to reflect a little bit on their own presentations and whether they've seen new ways of mixing and matching near-term technologies with real-world problems. And with this, I would like to invite Maria, please share with us your ideas on quantum machine learning.
Oh, thanks, Vedran, for the nice introduction. My microphone is working now, I hope. And so you will have to let me share the screen, if you don't mind.
Okay. You should be able.
Yes, great. Okay, great. And now I'm working for, so I'm kind of visiting my family at the moment. So I'm working for the first time ever on only one computer, which I'm not very used to, but I'm sure it will go well. Okay, great. Yes, welcome everyone to this session. Thanks so much for inviting me. I find the format very interesting. I'll give you a couple of precursors you need to know. So the first one is, you will see that the way that I will talk, what I will talk about is really, really different from what Reda will talk about after me. And this kind of disconnect is not just because we haven't prepared well, but it really reflects the disconnect at the moment from what industry calls applications and what science calls applications. And maybe, one of the things we can do after is really to look at how different they actually are, or where to go bridge from one to the other. So my role here is to give, the scientific side of how scientists think about quantum machine learning. It will be very general, but every now and then I'll dive a bit deeper. Why I'm saying this as well is that scientists are always skeptical, you know that. I mean, our job is to do critical thinking. And basically, I want to use this talk to make an argument that you can also think of as a little bit of a criticism of where the field is going at the moment. And this argument is that the tools we have in quantum computing, so I put in the subtitles, so complexity theory and small-scale prototypes, may actually not be enough to answer the really interesting questions, and maybe we're also not yet asking the right questions. So, so I feel that, and also like at Xanadu, we have very much this stance, and we discover the stance more and more about our own work, this feeling that we're already like diving super deep. We're making quantum convolutional neural network and analyze their trainability in barren plateau landscapes and so on and so forth. But there are a lot of questions no one has ever asked, like something for those of you who are in the field on quantum computing, why are we using RX gates and not something completely different? Or what are actually the figures of merit we want to be good at? Do we want models that generalize well on a small version of MNIST, or do we want models we can start to learn about and understand and really get like you know, a basic theory foundation for. So I think there's a lot of stuff we have to rethink. But, and this is the second part of the talk, because I'm not necessarily only a negative person, I wouldn't do this job in so many years if I wouldn't think that quantum machine learning has a lot of very natural and very, very beautiful connections. And so in the second part, I want to give you a couple of, you know, also as a means to show or highlight a couple of research fields. I want to show you where actually quantum computing and machine learning fit together very well, and where we can do this theory building from the bottom, or some examples thereof. Okay, that's it. I'm not entirely sure who's in the audience, but there might be some people also from industry. So working definitions, also to give you a bit of a timeline. So quantum mechanics, most of you know, so there's some kind of theory that makes us or lets us predict observations when we measure small systems. And this is very old. It started 100 years ago. Quantum computing around maybe 30, 40 years ago is information processing using these laws of quantum mechanics. Surprisingly difficult, and I don't think anyone who starts with quantum computing, or maybe this is a disappointment I had in my PhD, and lots of my students have it, that they always think everyone knows actually where this advantage of quantum mechanics for computation sits. But it's unbelievably difficult. I mean, you can spend a whole PhD on studying where non-classicality sits, and now to use this is a completely different, you know, pair of shoes. So quantum computing has come very, very far, but it's still very complex when we even say small things and easy things. Now, machine learning, if you would ask me to summarize what it is, I would say it's kind of extracting patterns of observation from a few examples, so that you can conclude to observations you haven't seen yet. Started also like a long time ago, and then had this obviously massive commercial boom. By now, I think people are a bit schizophrenic, no, not schizophrenic, they're a bit confused sometimes in machine learning, or we are a bit confused, I guess, because machine learning is actually a research field still, which is driven very differently, but it's also an industry. And sometimes the questions that the two should ask are different, but at the moment, they're still the same. Like, how can we build better and bigger models? And so also there's something very interesting about, you know, commercialization and actually fundamental research that's happening there. Okay, and then quantum machine learning is, in the definition that I use here, is basically solving machine learning problems. This could be classical machine learning problems. This could also be machine learning problems where the data comes from quantum experiments, or you could even think of quantum states or whatever, with the help of quantum computers. And I mean, the earliest papers are also like 20 years old or something, but I think so that this became mainstream and people know about this in the field of quantum computing started about 5 years ago. Classical machine learning experts don't know much about quantum machine learning, although I'm very happy to say that NeurIPS will have an invited tutorial on quantum machine learning this year. So there's a bit of interest and we see where this goes. Okay, cool. So the argument that I want to draw, as you say, I want to give you a feeling for why, basically just why it's such a hard problem to say something is working well in quantum machine learning, and why we might not have the tools yet that, you know, we need actually to find the good questions and the good answers. So I'm saying this in a very rough manner, and it's obviously simplifying a lot, but basically what we have as tools in quantum computing research is complexity theory and small scale devices. And most of you know that, well, complexity theory has been this traditional hammer that we always use to do everything, from fault tolerant, like old school quantum computing, the stuff that you find in the Nielsen and Schwank textbook. And so the idea here is that we don't know exactly how devices are implemented. So the only thing we can talk about is something very, very rough. It's the idea of quality being that the scaling of algorithms with the size of the inputs grows better or worse. So we have extremely intricate and very, very advanced, you know, tools in this part of the theory, but it's only one view on computation in general. And no need to say, those of you who do machine learning know that if you would only look at complexity theory and machine learning, nothing that's used in industry would ever stand the test of time, because, you know, neural networks optimization is NP hard, you know, we don't know, well, it's very hard to analyze why they work so well and so on and so forth. Okay, cool. And then on the other hand, we have near-term quantum computing, the NISQ era, and what we have here is small-scale devices. And for those of you who work in industry, like, so maybe just like a little bit of a table of like comparing the two, it's really a different paradigm of thinking. And quantum machine learning sits somewhere also in the middle, and you can sometimes define different approaches depending on where you are, what's your background. So obviously, these fault-tolerant computers, they have millions of qubits in abundance, you usually don't worry about it. You just worry about the scaling of algorithms. You need also a lot of qubits because you implicitly always think they are perfect, so your errors are corrected. And then you all have heard of algorithms like Schuld, Grover, HHL, algorithms where you can actually, these complexity theoretic arguments are very advanced and you can prove that they are better than some classical cases under certain circumstances. And the near-term computers are obviously like, in the NISQ era, we have only a few qubits, errors are still there. So when they get bigger, we start getting into trouble. And why I'm also saying this is that the algorithm design is extremely different in this near-term era. So we've got a lot of the algorithms we design, and I remember, so one of the people who introduced them is Jared McLean, and he once told me like how he found them. He was basically working with a hardware team, and he asked them, what can you do for us? And then they said, like, we can't do this. And he said, can you do this algorithm? No, we can't do this. This small case, no, we can't do it. And they said, what can you do? Well, we can tune some physical parameters, and then, we can implement some gates. And I said, why don't we use these physical parameters to optimize the algorithm? So we do not define or design an algorithm. We define and design a family of algorithms that depends on parameters. And by selecting or optimizing these parameters, you can optimize the algorithm or what the computer does. This is a very different paradigm, and you immediately see why this is like interesting for machine learning. And the research paradigm is really different. So in near-term quantum computing is really just run it and see. Sometimes to my taste, a little bit too much run it and see. So for example, sometimes I have users asking, I started, I tried to train a variational algorithm where I encoded data into our Z gates. Why does it not train? And then I think, okay, but our Z gates on a 0 qubit don't really do anything. So there's a lot of, cases where, sometimes it's good to actually do the maths and see what happens. Although just run it and see is also, it can get you places, or it can get us places actually. Again, on this topic, so I just want to give you so for those of you who are not in quantum computing research, I want to give you a taste of what I mean by complexity theory results. So this is from a beautiful paper on Hamiltonian simulation, a random example here. But you see there's always like these theorems, and they talk about like physical objects, and then they like estimate some errors and some runtime that scales with so-and-so. In the worst case, sometimes you have got error case analysis. So this is kind of the type of result we took in the olden days. And then nowadays it's really like you have a computer, you send either the algorithm, you run it on your local device. If they're bigger, you send it to remote simulators. You might send it to remote hardware, and you literally just get the result, and you can work pretty much like machine learning works nowadays in terms of practical applications. But obviously, as you all know, the computers are very, very small. Again, so to summarize this, what we have, and this is the important point I want to make here, if you look at all algorithms that can be run on a quantum computer, and this is obviously not to scale, at the moment, we probe two very, very small spots in this landscape. And if you're a student, or I don't know, at least I made this experience that the old quantum computing, generation that did these complexity theory analysis forever, they're often so used to it that this is not even, or I don't know, we're maybe not even aware of it sometimes, that this is a very, very small part of the world we can probe. And if you look at this like green bit here, then you can even see this one is biased towards algorithms that we can compare against classical ones, because not only your quantum algorithm has to be, open to your tools to understand it, but also your classical algorithm has to have some theoretical, access to it. So it's kind of a very small part of the world. Okay, cool. So now I want to just tell you, like in a very simple way and in a very simplified example, how to make machine learning quantum, and then try to formulate this argument. Why is it actually so difficult? The problem we're trying to solve here, like making machine learning better in some sense with quantum algorithms. Okay, so in the basic machine learning problem, so here in a picture, and I'll put it now in a bit more maths in the next slide. You've got some data, and you actually have two types of data. So you assume there is kind of data that you can sample. So the environment, the world gives you data. And you often also have like a small data set of examples from those samples you could get. Then you've got a model. In the most general sense, I think it's good to always think of models being supervised in terms of they take inputs, produce outputs like predictions or something. But a lot of machine learning is also about probabilistic model or generative models, where we only talk about probability distributions. But there is actually quite surprising how little formal learning theory we actually can do in this other case, or it's at least like a lot harder. And then we have a cost. And the idea is now, or the goal of machine learning would be in the sense to find the model that minimize whatever costs you define on all of the data you could see. And obviously this is not what you do, because all the data you could see, you don't have it available. So what you always do, you solve what I always call a proxy problem. So machine learning is very much about, you know, you kind of like solve a small problem, which is you find the model that minimizes the cost on a training set, on a small set of data. But you always know that by trying to solve this problem, you're not done when you solve this problem. You have to also hope or show that you actually like solve the original problem. And so this is like what I get back to in a few minutes, because this is really like the hardness of machine learning compared to optimization, where you just have to solve a problem and you're done. You actually have to now start reasoning about something that happens on a bigger distribution, which is really, really tricky. Okay, cool. The same for those of you who like it a bit in more equations, but it's actually the same thing. Sometimes it's actually quite beautiful to summarize it like that. And for this, I've picked now a supervised learning task. So this is pretty much what people study a lot in machine learning theory, machine learning research. So this is your data distribution. You remember this is the general distribution. And here in supervised learning, you've got inputs and labels. And now you've got this data set. So this is exactly what we had in the first block before. You've got a loss, called it like plots in the other one. So this is the same thing here, but the loss basically is just talking about like comparing labels for now. And now you have a model class. And now the task is to find a model that minimizes the expected loss over the data distribution. So you see here, for those of you who like maths, this is an expectation value. You say, how good is this loss if I integrate over all my data distribution and weigh basically each term here. And then this proxy problem is I minimize by approximating this integral by a sum. And this is obviously a big assumption, right? Because you could solve this problem and go very, very bad compared to this. Okay, why I put this out here is that I want to show you now this problem in a very like rough way of two big approaches of how we can make this quantum. In the first years, people did what quantum computing experts often do. They basically just took parts of whatever you do in machine learning. So this problem at the bottom here, so the practical application, for example, and you outsource it to quantum computers. For example, implement your neural network on a quantum computer. Okay, that's a bad idea. It's really like difficult to do that, but and hope that it goes faster. Or some neural networks you could put, anyways, yeah. Or do the optimization on a quantum computer, but the result of the algorithm is the same thing. So the only thing you gain here is speed. So you do, so in some sense, this is like quantum enhanced machine learning. So quantumness like accelerates an algorithm, but it's not necessarily like that quantum changes the problem or quantum computers make you learn in a very different way. And so this came very much in the second phase. So that started maybe like 3 or 4 years ago. There were examples also before where people like really changed the learning problem itself, but this one here is the most famous one. What you do, you change your model class to, for example, a class of quantum circuits or a class of models that are computed on a quantum computer. And then you kind of like try to solve this problem. But obviously by doing this, you change the entire learning problem. So you have to start from scratch. You have to ask, how good is this model class actually? How trainable are things? How, you know, like, so the whole machine learning machinery has to be rolled out by this. And this is very much, not always, but this is very much what people like do in near-term quantum computing. So they say, okay, this model class, let's just use a near-term quantum computer for that and see what happens. And because I don't have really a point where I can say this in general, but if you are researching in quantum machine learning, I see a lot of students who are super confused sometimes about how they really, I don't know, like which questions they really should ask about their models, or like how they really construct their models. And often they just follow the older generation, read papers and just use the variation circuits or the quantum circuit setups and designs that they use. But if you actually go through the literature and check what motivation there is to define this model class. So why do we use, for example, a circuit of C-knots and some, you know, rotations and some embedding and whatever, you will find that almost hardly any paper can motivate that. And I think when I talked about like a couple of questions we're completely blind towards is, at the moment, we consider this model class to be quantum computing in general, as expressive as possible. But machine learning is not any computation in general. It's a very specific model, and neural network is a very specific model. So here a little like hint towards if you are doing research there, I think one of the big open questions is, what is actually a model cloud of quantum circuits that's interesting? What are the figures of merit to look for here? And doing this systematically will be super, super useful. Okay, anyways. Okay, cool. And now towards this argument of why quantum advantages for machine learning are so hard to find. And I know that every advantage and especially commercial applications for quantum computing are hard to find, but I think machine learning has a completely different bar here. And I think we have to be aware of this when we think about commercializing or machine learning as an application of quantum computing. So what we're talking here, we have to show, I mean, somehow, whatever show means, that a quantum algorithm solves a learning problem well, while no classical algorithm can achieve similar performance, right? This is when we've really shown something like that. Now, if we are only armed with small scale devices and complexity theory, so the small scale devices, we can try them, right? But if you know the literature a little bit, like what we do usually, we take data sets and then we dump them down to something very, very small, and then we feed them into a quantum computer, run it. Often it's actually not that easy to get the quantum computer to run. You have to really think how your data looks like, how you scale it. And so it doesn't work out of the box anyways. But even if it works, so now when you write a paper like that, you're always like stopping afterwards and think like, so how do I compare this now? Do I compare this now to a neural network that has like 3 neurons or what? Or what is actually a fair benchmark for this? And obviously this problem is that if we benchmark small data sets, we never really get into the regime where learning at the moment happens and where learning is successful. So while these experiments are interesting, they're good, they will bring us closer to practical quantum computing, they're conceptually very, very hard to kind of, I don't know, systematically have like a result that whose scope you really understand. So then obviously there's complexity theory, and this is like our, you know, old school tool that everyone loves to use, and speed ups here and supremacy there. And this is obviously something that a lot of people do, and we have beautiful results out of this. But basically what happens in these results is the following. You change your machine learning problem into something absolutely abstract that's mathematically designed to be, you know, like good for quantum computing and fit into the theory that we already now know. So for example, if you want to know what I'm talking about, I really recommend reading those 2 papers. So this one here is more for probabilistic models. This is more for supervised learning task, where the authors basically take you know, something where we think quantum computers are good at, they turn it into a learning problem. Then, and this is the hard part, they show that a quantum computer can learn it fast and generalize as well. Remember, we don't only want to show you can learn something, we also want to show that what you learn generalizes well. So it's actually really tricky to show all those things. So then you've got these extremely artificial setups where you kind of, you know, proven that quantum computers can have an advantage. But, and this is like a panel about, you know, practical advantages, we're as far away of anything that's like useful as we can think of. I mean, so yeah, again, even if scientists talk about applications, and we're not even talking about applications in these very artificial settings, we're really, really far away of something that, you know, would actually make us take a quantum computer one day and run it on that one. Okay, so I hope you understand. So basically what I want to say, the tools we have at the moment, they only allow us to look at very small parts and maybe not the parts that are important. And I also mentioned that I think a couple of questions that we asked should be differently asked. And so in general, and we do this a lot at the moment at Xanadu, so I'm really happy because sometimes, you know, when you work in industry, you have to always like find the next logistics or optimization problem that you can solve with your quantum computer. But also in industry, I think more and more people realize that you need the breathing space to actually lay the foundations, because the foundations are not there yet. We sometimes think they are, but yeah, it's probably less than it. Okay, cool. And now the last couple of minutes, like a little bit more optimistic or beautiful. So if you actually go take a step back and you do not spend your entire time, or everyone in the team looks at what are advantages, benchmarking, practical things, you actually like start thinking about, so what does it actually mean to learn with a quantum computer? Or where does it fit into machine learning theory? How can machine learning theory actually help us? How do these frameworks fit together? Then you discover a lot of very, very beautiful ideas that also help us, you know, I would say that actually accelerate research to a point where just like continuing can't really do. Oh, and I'm getting my dinner here. Okay, cool. So one of these fields, and I guess that a lot of you know about this very well, and I've spoken about this already, so there's a second approach, we use a quantum algorithm as a machine learning model. And for those of you who do quantum computing, so here's how it works from far above. So there's two options. You can use it as a sampler, a generative model, a model that produces data, or as a model that labels data. I told Vedran I've got a big clock in this room, and it would sound exactly when it's 6. I know I've got like only 10 minutes left. So what you do basically, you take a data point, a data input, and you encode it somehow in the quantum computer. There's a lot of work, and I'm a big fan of this kind of work, that analyzes actually how the encoding is extremely important, because the encoding already solves the machine learning problem in some sense, because a quantum computer does linear processing. Linear processing doesn't have a lot of power in separating, classes of data. So the encoding is really important. You process, for example, with a trainable circuit, then you measure this whole setup, you repeat it a lot of times, and you post-process, and you get some kind of result, an expectation of a measurement. What is the average of the first qubit being in state 1 or something like that? And this you interpret as your prediction. And now you can kind of use your quantum computer for supervised learning. In the generative modeling case, it's actually a lot more kind of like natural in some sense. So you use your quantum computer, in some sense, you use the processing that has this inherent quantum randomness as being like kind of a random seed of a generative machine learning model. Generative models are models that produce data. And then you measure, and then you get data samples from it. And now you can also think of how can we, for example, tune parameters in our quantum computer to get specific distributions. So here, this is like kind of so an idea of the first part. So we really like implement it in like 1 qubit. I've plotted here kind of some data set. I encoded the data point, which is like a scalar value by an Rx rotation into a qubit that I represent here by a Bloch sphere. So I don't encode in real life the entire data set. I just plotted it so that you see where everything lands. Then the rest of the algorithm, I just say, is any rotation with a couple of parameters. They rotate this data set on the sphere, and then an RZ Pauli Z measurement would have almost slice through the sphere. And I also wrote down how mathematically speaking this model looks like. So again, if you do quantum computing, there's no magic. There is actually, in the end, usually some trigonometric functions. So this is a model class. This is math, right? You can write this down. You can often look into this. And for example, this is the quantum machine learning model I've created here. So first of all, this is actually quite sweet. We can actually use physics really to represent models. The second point here, and I only highlight this very briefly, is this idea that quantum algorithms can actually be plugged into deep learning training pipelines. And to summarize this, what I mean by this is, so modern machine learning is more than just only learning. It has also a lot of software and technological solutions that have to do with automatic differentiation. What that means is that you can write an algorithm or computer program down. And if your computer program, like a neural network, depends on parameters, you can do a huge computation, and then you can compute gradients of your output with respect to your parameters by just going back or backpropagating, or how can I say, by automatically computing gradients of every node and chaining them together. So basically your computer can optimize because your computer can get gradients out of very, very complicated computations. And now here's the question: what if you plug in quantum computers in here? And then obviously what you need is gradients of quantum computations to get kind of your chains of gradients flowing. And it turns out that we can get gradients out of quantum computers. It's not very efficient in the sense that it scales linear in the number of parameters. If you think about the number of times the computation has to run. It doesn't scale as good as neural networks, but it's still possible. And this has enabled us, nowadays you can, in frameworks like PennyLane or TensorFlow Quantum, you can literally have a huge neural network and then put a little quantum layer and see what happens if you train the quantum layer. The theory behind this is really beautiful. So there's a lot also to do in here. Last but one highlight is a topic that I love very much. So this is the idea that quantum circuits, in the sense of them being used as supervised learning models, are actually linear models in feature spaces. And this might not sound so crazy to you, but maybe you get a feeling for this when I tell you a little bit the idea of linear models in feature spaces and what it means to machine learning, unless you know it already. So in every textbook, you always start with a machine learning model could be a linear model, and statistics 100 years ago has looked into this. So an inner product of a data point represented as a vector and some weight vector that you can then train. And the beauty of these linear models is super simple. They give rise to linear decision boundaries between data classes and stuff, but you can use convex optimization to train them. complex optimization means simple optimization. We know a lot about this. We have guaranteed solutions and so on and so forth. Now, in classical machine learning in the 90s, people have noticed, first of all, you can obviously like map your data in high dimensional spaces and have linear models there. You still get complex optimization, but now in high dimensional spaces, and optimizing in high dimensional spaces is really bad. But what happens is you can actually change your model ansatz a little bit and only access this high dimensional space through inner products of things. So what I mean by this, you have a very, very easy access to this space. You never need to really like optimize in this space, but you can optimize in a much, much smaller space. So in some sense, you still have simple optimization problems, but they're now a lot more powerful. And you can show indeed that, you know, these methods, and they're called like kernel methods, they can optimize a lot. And so now it turns out, and maybe you got the hint when I showed you this block sphere, that this is really what's going on in quantum computations. And this is now for people who are very, you know a little bit about the formalism, and I'll leave it at that as well. So if you, as I said before, you write down your machine learning model as being, you know, like the expectation of some observable. So M is here an observable. I use the density matrix formalism for a very, very good reason here. And I have encoded data into my density matrix through some quantum routine that embeds like data into the state. It turns out that the trace of two matrices is an inner product. So you can very, very easily mathematically understand this part here as a vector that, or a map that maps data into high dimensional spaces, and this one here as a trainable vector in a high dimensional vector space. And so this like unlocks basically 20, 30 years of deep, deep machine learning theory, and theory that knows how to talk about generalization, talk about this proxy and the original problem very well, immediately map it to quantum computation. So this is really a cool, I think a very cool result. And then the last one is just as a highlight, we also know quite a lot about the other way around, but people don't speak so much to each other in these two communities. So the people who analyze how to represent quantum states often use neural networks. Not only tensor networks, if you know those, but also they start using neural networks. So, and whatever they find has obviously a lot to do with what we find, because we are kind of trying to do it the other way around. So also have a look at this type of literature. And then I thank you, and wanted to like end with this picture because I really like it very much. I kind of recently dug it out. That was in July 2016. I think it was one of the first, so in 2015, there was a workshop at NEURBS of quantum machine learning. It was one of the first workshops that there was in the world. And you see our wonderful host here. So like we are friends for many years, and you see a lot of like really like fantastic people who have done a lot of the early work. You see Peter Wittek here, who we lost, you know, in a couple of years back. Yeah, and those were good times. And, you know, now the community is a lot bigger, but it's still like lovely people in there. Okay, cool. If you've got any questions, shoot away.
Thank you very much, Maria, for your wonderful talk, and for sticking not only on time, but being faster and using up less time that you had allotted. It just opens up more room for our audience to ask you questions. And maybe to clarify, at this point, I would predominantly invite technical questions about technical aspects of Maria's talk, and then more general questions about connecting, you know, quantum computing in general with real world applications. This we can maybe defer for the end, the closing Q&A session, for which we'll have more than 20 minutes. So does anybody have more technical or more particular questions for Maria about her part of the talk? So in the Q&A session, in Q&A panel, I see we have one question from Mehmet K, who asks, how would you visualize a quantum algorithm? Because he feels that the gate things are hard to understand. Is there a way to map quantum algorithms with basic algorithms within giving you knowledge of the binary world?
That's an interesting question. So, I mean, people, I think the most generic way is, you know, something like a block sphere visualization. So there are higher level block sphere visualizations, but I think you very, very quickly get lost in visualizing what happens. And so I think there's two answers to this. So the first answer will be, if you have a question, break it down to 2 qubits and calculate that. Take Mathematica or something and really do the, you know, symbolic calculation and get functions out and really see what happens there. And I think this is a very good way. or you could look at a few qubit system and see how the state evolves. And don't be embarrassed. I find, not more qubits doesn't mean we understand them. Sometimes like 2 or 3 qubits are really enough to understand what is actually entanglement, what's really happening here. And then if that's not enough, I think you have to go deeper into mathematical tasks. So for example, I tell you one visualization that I really love. And that is, so I don't know if you're aware of this work, if this is like your background, but you can write a lot of quantum circuits as Fourier series. And obviously Fourier series is just like an expansion in a basis. So you have coefficients. And it turns out, I mean, you can write any function as a Fourier series or most any function, but the Fourier coefficients, there are only very few. So you can literally like plot them. And sometimes, so what we've sometimes done is to, and I think Penny Lane has actually a function for this or tool for this, where you can visualize like the Fourier spectrum of a circuit. And sometimes you can get something out of this. So then you have to like find those kind of visualization strategies. But I wouldn't know a better one. Good question.
Thank you, Maria. So the next question that I have is something that I believe you probably heard before. Is converting classical data to quantum states and then applying quantum machine learning a hard bottleneck for you?
No, not necessarily. I mean, it depends, right? So for example, if you want to find an algorithm that runs in logarithmic time in your data, then this is a bottleneck, right? Because you have to touch your data and encode it. But I mean, this is maybe a crazy idea anyways. Other than that, I mean, you can just like, for example, in this typical thing that people do, you just like take a feature in your data vector and encode it into a rotation gate, for example. And this is just like, as many features as you have, you need as many rotation gates. So this kind of scales well enough. So this is actually not a problem. The bigger problem is to choose what embedding you take. And I mentioned that this has a really immense influence on how well the algorithm works. And we hardly know. I mean, there's a couple of papers that analyzed, what's the quality of embedding on other, but it's very, very hard to even know which one is a good one. And this is the big open question. So the embedding, which embedding to take, which circuit you take after the embedding, if you want to do these like variational circuits, for example, I do believe we do not know why anyone is doing what.
Thank you. We have a next question about the future. What do you see as the key elements of the next QML models?
Yes. A good question, and I'm only aware of this question so much since a couple of months. And if you work in industry, you sometimes in a couple of months you don't get really to sit down and do research. But my pitch is the following. So if you think, for example, of what was the building block of a neural network, that was a perceptron, right? And so perceptrons are just these small models derived from neurons that have this integrate and fire principle built into them. And people in the 40s already, back in the 40s, built models out of these perceptrons and were super keen and said, oh, we have machine learning is solved, AI is solved, kind of. And so obviously then there was a lot happening. And nowadays people always turn perceptrons into quantum perceptrons and then see where they get from there. And I think I can answer your question maybe with saying, so what we need is, instead of trying to quantize a perceptron, so take some maths that's completely alien to like quantum computing and try to like squeeze it into our formalisms, I think we have to ask what role had the perceptron in neural networks. And it was kind of a small system that people could study well, where learning was understood. So long story short, I think what we need is a small building block, maybe to get back to the first question, that we can visualize, or where we can gain understanding. So I think the next tools that we need are things that help us to understand and not to beat classical machine learning. And I think only 5% of the papers you see, or 1% of the papers you see, do that or are aware of that. So yeah, and I sometimes think that without this, we won't get to a place where we can actually commercialize machine learning if we want to. Yeah. But we can discuss this a bit later as well.
Thank you very much. And I think we have time for just one last question from, is the quantitative effect of quantum noise on learning known?
And there were a couple of really nice papers on a very, not simple, but like, a very theoretical learning problem. Vedran, I think you know this kind of work as well. It was like from a couple of years back, where people have shown, so it was like a question of sample complexity in learning from membership query setting or something, where you just have like a couple of bits and then you do, some very typical quantum algorithms on those, where someone had like the idea that noise harms classical machine learning, you can show that something becomes unlearnable under noise. It doesn't harm quantum machine learning, but you are not talking about quantum noise, right? It's actually a completely different question. So there I wouldn't know, yeah.
I understood this question really had to do with what happens when you run it on a real device rather than a simulator, and then what happens. That's my guess. Thomas can correct me if I'm
okay. So noisy devices obviously just kills everything, and everyone who's run on hardware is like, okay, you kind of like, you have a couple of gates. If you have more than, I don't know nowadays, like I've run the last times I've run was like 1 or 2 years back, but you know, if you've got more than 20 gates, you can throw away your model. So more theoretical studies, I've spoken to Nathan Lieb a couple of times. He had a couple of ideas of really if there's a scaling, like how for example, your decision boundaries or proximity to decision boundaries like scales with kind of like affects the, but I'm not aware of like some big theory that everyone knows and that's like kind of understood. So good luck if you want to look into this.
Thank you very much, Maria. I think this is, we're now spot on time for our next talk. I would ask all other questions which have not been answered, just keep them here until the end of the next talk, and then we'll try to answer everything that we can. And at this point, I would like to invite Reda, who, as I briefly mentioned, is our expert from TotalEnergies, all things reinforcement learning and dealing with uncertainty. Please, you have the floor.
Okay, thank you very much. Let me share my screen. Okay, so I think you are able to see my screen.
Yeah.
Okay, so thank you very much for this invitation. My name is Reda Alami, and today I would like to present you a use case, industrial use case that we have at TotalEnergies, and I believe that it is a central use case where we can use machine learning techniques and maybe quantum to optimize it. So it is a joint work between me, Maribel Badr, who is an intern at TotalEnergies, and Antoine Bertonchello. And also this work will be presented at NeurIP's workshop entitled Ecological Theory on Reinforcement Learning, which will take place in December of this year. Okay, so as we know, the reinforcement learning has been a success in games, for example, in Atari, where we have been able to show that the deep network has reached...
Sorry, Reda, for interrupting. Have you switched slides?
Yeah, I'm switching the slide. No?
Yeah, because unfortunately we see the background, don't see the full screen. We only see the window of your viewers. So I think you need to share either the entire, I think you need to share the entire desktop.
Okay. Okay, let me see that. Can you see now?
Yeah, perfect. Thank you very much.
Okay, excellent. Okay, so as I have mentioned, the reinforcement learning techniques in machine learning has been a success in games, for example, in Atari and in Go. So it's been in Atari, we have been able to show that deep network approaches can beat the human performances. And in Go, Google DeepMind has been able to build a very powerful algorithm based on the Monte Carlo research in order to beat Lee Sedol, which is the world champion in Go. The question is that today we have this success, but can we be able to use reinforcement learning to optimize industrial use case, for example, the inventory management? Can we use RL in order to have a perfect control of inventory system? So now I will follow this this plan in order to show you how we can do that. So I will start with an introduction, then I will present the problem formulation. I will quickly present an overview of how we can optimize inventory management. Then I will show you the proposed solution, and we will see the results and go to the conclusion. So first of all, why the inventory management is important. So in every inventory system, we have to face a lot of uncertainties. And basically, these uncertainties comes from two sources. The first one is the demand, and second one is the lead time. If we are able to control the demand and lead time, we'll be able to control the inventory system. The problem is that if, for example, we have a very high stochastic demand, we will take the risk to have a lot of shortages. And in this case, the service of the company will be very low, will be very bad. In the meantime, if, for example, we have a demand which is very low and also the lead time, in this case, we'll have an inventory which is an excess in inventory. And in this case, we'll pay a lot of costs because we have a lot of elements in our inventory. So we pay a lot of costs. The question is, how can we find a balance, an equilibrium between having an excellent service level, which is reached when we don't have shortages, and how we can minimize all the costs of the inventory system. And by the way, if we find this balance, we will increase the company performances. Okay, so today, in order to solve this problem, we have inside of the art a very basic heuristic, which is called the NISQ strategy. It's basically a strategy that tells you if, for example, your inventory level is below a certain threshold, which we call S, we replenish. We take a replenishment of Q elements, and then we'll wait until we are consuming the element that we have in our system. And then if we have, for example, the inventory level which is below this new threshold, we have to replenish. So the question is, first of all, how can we choose smartly the two parameters, S, which is the minimum level, and Q, which is the replenishment quantity? And secondly, how can we be able to guarantee that using this we can face every uncertainty of our system? So this basic heuristic, unfortunately, is not able to capture every demand and every lead time because they are stochastic, and this heuristic is basic, and the parameters are fixed. And we have also seen that also dynamic programming will not be a solution, because in order to use dynamic programming, we have to know the transition kernel and the reward function of our environments. And also it is very limited where we have a huge set space. So because of these two reasons, we would like to use something better, something more interesting, which is reinforcement learning. So what is basically a reinforcement learning is a machine learning techniques that allows an agent to interact with an environment, basically the inventory system. This agent has, at each time step, it has to take an action. Based on this action, the environment will change its states, and it will give a reward to the agents. And this is done sequentially. So at each time step, the agent chooses an action, it take a reward, then it chooses an action, and so on. And the objective is to maximize the cumulative reward in the long run. So this long run, it is called technically the horizon. So let's say the horizon is, for example, 1,000. We want to know, we want to reach after 1,000 time step the maximum cumulative reward. And what is very interesting is that reinforcement learning can also always be applied in a case where a goal can be modeled as a maximization of a cumulative reward. So in our case, if we make a link between the reward and the cost function, we can maximize the reward, and by the way, minimize the cost function. And in order to do that, in order to reach the optimality, we have to deal with what we call the dilemma between exploration and exploitation. The exploitation is that we will rely on our past observation of the system and then take the best action. The exploration mean that we will not rely on the past knowledge, but we will take a risk to take other actions. So you can see that in order to reach an optimal policy, we have to resolve this dilemma. We have to know when to do exploration and when to do exploitation. So basically, what is the problem formation that we can do is that at each time step, our manager, our inventory manager, has to satisfy a stochastic demand. So in order to do that, he has to choose how many items to buy. So we'll consider that the items of our warehouse are independent. And so at each time step, we have to choose the number of items to buy. Then because of the stochastic delay, basically we will not get the item instantaneously, but we have to wait for a delay for a time step which is called the delay. After some delays, we will receive the item in our warehouse, and then we have to see if it is enough or not to satisfy the stochastic demand. Okay, so basically our objective is to minimize the cumulative cost. So we can consider that the cost at some time will be divided into three costs. The first one is the holding cost, which is related to how many items we have now in our inventory. The second one is the penalty cost. So it is related to the shortages. So whenever we are not able to satisfy that demand, we will incur a loss, which will be very huge in order to oblige the agent to not be in this situation. And we'll also have naturally the ordering cost, which is related to how many items we have bought at some time. So our objective is to find a way in order to choose the best the best ordering level at each time step in order to minimize this cost. So I will explain some assumptions that we have done in this study. So first of all, we'll assume that the items will be treated independently. So we will have one agent per item. So this is our first formulation. The second is that the lead time and the demand are stochastic, they are not chaotic. And to facilitate the analysis, we'll consider that the distribution is a Poisson distribution. We'll also consider that we will not have the demand at each time step, but the occurrence of the demand will follow a geometric distribution. And we'll also consider that these two distributions are stationary to see how we can deal with this case. We'll also consider that the inventory capacity is finite. So the maximum, our warehouse is not infinite. So we have a limited number of items in our inventory, and we will also consider that we are not allowed to have shortages. So if one demand is not satisfied, we will incur a very huge penalty. So in order to use reinforcement learning, we have to model our environment as a Markov decision process, which is basically 4 tuple elements. The first element is the state space. We have to choose that the state vector will contain these 5 elements. The first element is the inventory level. Basically, it's how many items do I have now in my system. Second one is the on order. So the basically is how many items do I have ordered in the past. D is the demand that I have observed. The inventory transition is the number of items that I will receive after the lead time, and O is the ordering level that I have done. And basically the action will be the orders. So how many items do I have to buy at each time step? And as you know, because our inventory level is finite, it will be between 0 and the maximum level. Then, because of the stochasticity of the demand and the lead time, the transition kernel will be unknown, unfortunately, and we'll consider that the reward at each time step will be basically an inverse of the cost function. So basically, it will be minus cost t. Okay, so in order to we can detail how this inventory is working. So at each time step after receiving the inventory transition, the inventory level will take its following form. So basically, we will add the inventory transition to our actual inventory level, and then we will remove from this the demand that we have now. The inventory transition will be basically the on orders that I got from the last lead time, and this on order is basically the number of items that I bought from the last lead time until now. Okay, so basically, what are the overview of the inventory management that you have now in the state of the art? So first of all, our setting is decomposed as follows. So our network is serial. So we don't have a lot of stages in the decision. So the only decision that we have to take is that at each step we have to choose the action, the number of items to buy. We'll consider that the products are single because we assume that the items are independent. The lost sales are described by the unsatisfied demand. Our goal is to minimize the overall costs. The uncertainties are described by the demand and the lead time, and we consider that the horizon is finite. In the state of the art, there is some good solutions of this kind of approach. So basically, the easiest solution is what we call Q-learning, which is the easiest reinforcement learning technique to do. But so I can explain quickly what is the Q-learning. So the Q-learning is a very basic solution of the reinforcement learning. It is based on what we call the Bellman equation. So the idea is to be able to give to each state action pair a Q function, which is a Q value, which is basically the importance of an action in a particular state. And the objective is to fit this Q function in order and then to take the action that maximize this quantity. So in order to do that, we have to explore all the states and actions. Then we have to fill a table, which we call the Q table. And after that, in order to take decision, we only have to take the argmax of this function. So what is interesting is that we have shown in the state of the art that this Q learning will always convert to optimal policy when the discount factor is less than 1. So this is a good new. But the problem is that there is some drawbacks. First of all, in order to do that, we have to keep the memory of all the states and actions. So if we are in a case where the states is very huge, it will be very difficult. And in order to do that, we need a lot of time. So for a realistic case of ours, it will be difficult to do it. So we have chosen to do something different. Basically, it is the work from Volodymyr Mny in 2015, which is basically it's a Q-learning but combined with a neural network. So instead of using the Q table, we'll use a neural network. We have chosen it because this algorithm is very popular in the literature. It has achieved optimal performances in the Atari game, and also its performance is always steady in comparison with policy-based, where this approach can be less steady. So basically, the DQN is as follows. So at each time step, we will recover the states of our inventory, which is basically the inventory level, inventory transition, on order, demand, and the order at last time. Then we have to choose what will be the actions to take. And in order to do that, we have chosen to use what we call the epsilon greedy exploration. So we'll take actions randomly with an epsilon probability, and we'll take the best action that we have built using the neural network of the Q function with probability 1 minus epsilon. So with high probability, we take the best action that we got in the past, and with a very low probability, we take an action randomly. So I will show you some results, some initial results that we got. So first of all, I will explain the experimental setting. So we have simulated an inventory system whose capacity is 70. The lead time and the demand will follow a Poisson distribution. For example, the lead time can be a Poisson distribution of parameter 6. The demand will be also parameterized with a probability. So we'll say that at each time step, we'll have a probability 1 minus p to not have any demand, and with a probability p to have a demand. The horizon will be equal to 500, and we will have 2,000 episodes in order to simulate the convergence of our algorithm. In terms of parameter tuning, the deep network is a hyperparameter algorithm. So we in this study we have chosen the same hyperparameter tuning that the one that has been chosen by Volodymyr Mny in his work on Atari. So what is interesting is that the epsilon parameter which control the exploration will decay exponentially from 1 to 0.001. We do this in order to give more possibility to make exploration in the beginning, and then we will give more possibility to do exploitation. So the first result that we got is that, for example, here, if we take a lead time following approximate distribution parameter 6 and a demand following approximate distribution parameter 7, we can see that the learning curve of the DQN is below the min-max, which is basically the SQ strategy. So we can see that here we reach a better cost than the min-max. In terms of unsatisfied demand, we can see that the number of unsatisfied demand of the DQN is lesser than the one of the min-max, which is very interesting. And here we have plotted the variation of the demand, which is in green, and the variation of the inventory level followed by the DQN against the inventory level followed by the min-max. And as you can see here, using DQN, we are able to follow this demand, while the min-max, the SQ strategy, is not able to follow it. The SQ strategy is using a worst case solution, and in this case, we are not able to follow the demand, but using DQN, we can do this. We have noticed that using the DQN, we are able to reduce the costs by 38%, which is very interesting. And we are also able to reduce the unsatisfied demand by 78%. Then we have changed some the parameters of our demand, and we noticed that we are keeping the same behavior. So the unsatisfied demand flow reached by DQN is lesser than the min-max, and also here we can see that the inventory level of the DQN is following the one of the demand, which is very interesting. And statistically speaking, in this case, we are able to reduce the overall cost by 25% and the unsatisfied demand by 94%, which is very huge. Then the last experience, so we have increased the demand rates, and as we can see, we are keeping the same behavior. The unsatisfied demand are lesser using DQN, and the inventory level is following the demand. And statistically speaking, we are reaching a reduction of 20% using DQN and 96% of unsatisfied demand. So globally, the DQN is working well on this very simple version of this use case. What we want to do now is to extrapolate this study for multi-product setting. So we consider that we have a lot of products instead of one. So in this case, we will be interested to use what we call multi-agent RL to see how can the agents collaborate to minimize the costs. In this study, we have simulated the data. What we want to do now is to collect the real data from the company and to see if our model is working well or not, and what will be the challenges that we have to face. I can imagine that one of the challenges that we face is that the demand will be non-stationary. Maybe we'll have some trend at some time, and then the demand will change its trend. Then we will communicate with our supply chain department in order to build a more realistic environment in order to reach this the minimum cost of this management. And maybe we will also see other techniques. As I know, the DQN has been improved by using other variants like the Rainbow DQN, which has outperformed the human performance in Atari. So it will be very interesting to see how this algorithm will perform in this setting. So globally, this is the overall view of this use case. So if you have questions, or if you want to have some more details on this, feel free to ask me, and maybe we can see a way to use quantum ML in this setting.
Thank you very much, Reda, for your wonderful presentation. And now we're entering the last phase of today's webinar, where we, of course, answer all the questions that we may have from the audience, but we will also try to inspire a bit of communication between our two invited speakers. So maybe just to, while we're waiting questions for both of you, maybe to ask just both you, Reda, and you, Maria, right now. So Maria, you yourself foreshadowed this. There's going to be a large gap, right, between the real world problems and all these infinitely many little moving parts that are happening, right, with respect to the simplicity of theory, even when it's very complex. But do you see any point in this type of research where you think quantum models could play an interesting role from your point of view?
Yes. Before I say, I warned you already. I'll post a link. I promised my colleague I would post a link to the residency program, so we've got an internship program at Xanadu, if you want to explore this stuff a bit more. However, to answer your question, I think actually that Reda's talk was, so I think I can kind of like visualize it to the point I try to make with exactly what he said. So if you're now sitting and you are the poor student that has been hired by TotalEnergies to do the quantum version of these problems and solve them, right? Or not the poor student, but maybe the fortunate one. But so now you sit there and you have this big problem that's solved by, you know, even the problem setup is really big. And now you use, in the best case, a deep neural network inside this problem setup. And reinforcement learning is a lot more complex even than supervised learning. And now you have to basically show, you know, somehow with complexity theory or whatever, how good this problem is theoretically. And then you have to show that there's a quantum problem that's better. Even to show how good this problem is, I would say almost impossible. I mean, look into machine learning. These results are not even, in some sense, I mean, in small steps existent there, but definitely not in the big package. The other option you have, and I think most people then do that because the first one is so impossible, they use a little small quantum computer, a variation circuit, somewhere on the cloud, IBM, Qiskit or whatever, and then they plug it into the deep neural network somewhere, and then they compare the results. But obviously, you have to kind of dumb down your data, you have to do all those steps. And then, as I said, often you do these studies, in the end, you've got a couple of plots. One is better than the other, but so what? Where's the scope? What have you learned in some sense? You have made this work, that's amazing. I mean, that's really hard. But do we systematically really understand if we should use a quantum computer or not? I would doubt that. So there's the third point that I then try to make is this: if you have a Markov decision process that you try to like now use with reinforcement learning, couldn't you simplify the problem extremely and use the simplest version of a Markov decision process? And, you know, they are very similar to Markov chains. We know Markov chains have something to do with quantum walks, you know, and try to find this connection in the simplest model. And for now, throw away your data, you know, your big data sets, and use very, very small data, and just try to understand this a little bit of, if your transition matrices have quantum effects in them, if they entangle something, what happens actually? So that's the kind of the entire thing. So while Reda, I won't, you know, I can't like offer you any quantum algorithm now. I think the approach to solving this question is really to simplify. Sorry for talking so long, but yeah.
No, thank you. This is why we would like to have you here. But maybe I would like to ask then Reda as a follow-up on this. So Maria, your point was that you're interested in what kinds of function families these quantum models actually build, right? And to really understand them, what they could be good for, right? So maybe the question for Reda would be, in his research, there are many different kinds of neural networks, right? There are different architectures, and this is one of the hyperparameters of your model.
Yeah.
In your experience, does it matter, right? Because I have checked your list of hyperparameters, and in fact, I did not see the specific choice of the neural network as a listed thing.
Yeah. So here, basically, in reinforcement learning, we are choosing perceptrons. Basically, they are perceptrons. For example, in the deep Q network, we have two perceptrons. For example, in PPO, the proximal policy optimization, we have two perceptrons, one for the actor, another for the critic. So basically, in reinforcement learning, in this kind of use case, we only use the perceptron neural net.
I mean, do you mean that the activation function is a step function that in particular? Yeah. But what about the depth and connectivity of the network? Does that influence performance?
Yeah. So generally, we would like to use a neural net which is not very, very deep, because if we use it, it will be more difficult to describe our state space. So generally, in this kind of use case, the neural nets are not that big. So we can have a multi-layer perceptron with, for example, 64 hidden layers, which is generally sufficient for that.
Thank you very much. So we have at least one question from the audience, and I would really like to invite the audience to ask everything that's on your minds. I see that Maria has already been busy responding in the background in the chat. The question is, that hyperparameter tuning is very time and space consuming in deep learning. What are your thoughts about the applicability of quantum computing to hyperparameter tuning?
Yeah.
Yes. Do you want to take it, Reda?
This is difficult for me, this one.
Yeah. This is actually, it would be nice, I don't know if you can probably not unmute yourself, but it would be nice to know exactly what you think about. So, because I only have very naive thoughts about this, because if you want to tune hyperparameters, every time you have a new candidate for the hyperparameters, right, you have to kind of evaluate what happens. So you probably have to like do the entire training and then like evaluate. And at the moment, I'm not entirely seeing how you think of outsourcing this. You can't outsource this really to a quantum computer because you want to know what's the right hyperparameters for your classical model, right? So in some sense, what part of this would then be done by the quantum computer? Because the intensive part is that every time you have a new candidate, you have to now evaluate how good it is. So I'm not entirely sure, but you probably have a cleverer idea of this than I'm, I don't know, making it out to be. But again, to me, it sounds like, again, a very, very big problem that you're trying to do, a problem where machine learning is encapsulated in one small part of an even bigger problem. And this is, again, the thing that I'm trying to do at the moment is to go to the small problems and see what we can do there, because otherwise you get lost very easily. However, I'm keen to learn more. So if you want to type again, you know, what you mean?
Perhaps Jeffrey will make his comment. So one thing that I find interesting, Reda, in your talk, which is kind of very different from what Maria was talking about, but she on purpose has wanted to have this very clean theoretical perspective and wanted to get to the bottom of the answers. You reported 25% improvements and 94% performance, which was, you know,
huge.
And you said it was huge, right? I mean, if you turn it into euros or dollars or whatever,
no,
Bitcoin,
it will be a lot of 100 millions of euros.
Right, and
if it's working in real life, because
and this is right. So this is the real world, and then I look in contrast when Maria is looking at. She wants proofs of exponential separations, right? And this is the thing that we would really like, because then we know, right? Then we know.
Yeah.
That's a dead thing. But I'm always somehow hopeful that quantum computing, at least eventually, is, I mean, when it becomes not that expensive.
Yes.
I mean, give me, you know, 5% more accuracy for a really difficult problem of, I don't know, identifying early stage cancers in the brain, and we've justified all of it, right? In a way. So Maria, what would you say about this? I know this is a very optimistic picture.
I do not. So I read the other day. I read on PX Quantum or something. There was a perspective on, you know, why quadratic speedups are not enough, and you know, the community talks more and more about this insight that quadratic speedups, due to the overhead of quantum error correction, won't be enough. I'm actually not an expert enough in this field to really understand if this is true or not, because I would also always say, like, you know, one day it will just be a little bit better and that's enough. So I think more like at the moment we cannot say there will be this 5%. And so this is something I would also like to ask you, Reda. So let's be honest. So I know machine learning experts are expensive, and they might be more expensive than quantum physicists these days. I mean, probably by far. But I mean, if you can get this out, can't you get this percentage out by really hiring, you know, a very, very senior person, paying them a couple of million a year, and kind of making them tune bigger and bigger neural networks, and then, you know, getting a lot of GPU space. So I'm wondering sometimes, so for example, if you have industry connections, you very often, like, they are expecting you to do something better, but often you actually end up tuning their classical models first of all, and they get so much better that, you know, you realize that or would you say there's actually a margin that at the moment classical computers, you just can't get past this, even with the best experts and the biggest teams in the world? So that would be interesting, I think.
Yeah.
So maybe just to summarize your question, right? So Maria's question was, can you not get this 5%, which equates to 100 million a year, by getting 3 people paid 10 million a year to squeeze it out of a neural network, right? Why does this not happen in practice?
Okay, so we can do it. So we can for example hire a lot of genius in the world to do that. But the problem is that first I have to convince the digital factory that this is the way to go. So it is a management problem that I have to solve. We have to convince the others that this problem will bring a lot of millions of euro to the company. It can be a way. Yes, for me it can be a way to solve it. Yeah.
So then obviously, so for us, then the bar is a very moving target, right? If you work with companies and then you show like, oh, our quantum algorithm with 2 qubits is 2% better or something, you know, like, but then you start working on the classical algorithm and bigger is better. At the moment, we haven't seen an end to bigger is better. And so, yeah, it might be. So this is why maybe we can actually lean back and say, okay, we can't compete at the moment. Let us just understand and then compete if we want to.
Yeah, this bigger is better trend. I mean, theory says this should end at some point, right? And at least in reinforcement learning, if I'm not mistaken, we've seen that this does not really hold. They've not managed to get better performance of these DQN networks by just piling on more parameters and more depth. But it is a little bit different than classification. So maybe that's something interesting. If I can maybe ask a little bit more basic questions. So Maria, you have been hinting that we're maybe asking the wrong questions like all along, or maybe too ambitious questions. Do you have any other ideas of what kinds of questions we haven't asked that we should be asking right now that you would like to share with us?
So one of the things, I think this is Reda, I don't know if you also like sense this, but in the machine learning community, especially in the research part of the community, a lot of especially the old guys are starting to be angry about that we think we have all the resources in the world. Right, this bigger is better, that at some stage it doesn't scale. And I think this is also like, you know, comes from like climate change movements and this idea that actually, so there's a beautiful paper from the creator of Keras, Francois, I forgot his name, unfortunately, but about what actually learning is. And when you define it, you shouldn't just define it, it's learning from data. But good learners, they don't just reproduce or emulate, they actually learn efficiently from data. So if you see a cat flies, you know what it is, right? And so I sometimes wonder if the figures of merit, if there are speed, generalization, whatever, performance, blah, 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 number of qubits you use, if there's actually a figure of merit in machine learning that we should try to beat, because at some stage it has to be beaten, and which is efficiency. How much data do you need? How much training do you want to spend? So not scaling, but really just that.
Yeah, there's a challenge which is called how to learn how to learn. We have to know how to learn. Yes, you're right. Maybe the way to go is not the bigger the better, but smarter the better. For me, I think it will be smarter the better. Yeah.
Okay, while we're waiting for questions from our viewers, I have a little bit of a strange question for you, Reda, maybe in the problem that you described. So, so one of the main problems that you have is the uncertainty, right? That you have a completely stochastic system, and it's not so much about being heavily Markovian, right? It's just a random thing. Are you familiar? Is there any relationship between these types of problems and like the problems that people encounter in quantitative finance? And like modeling stock prices and things like this?
You're right. So I have seen some recent work on applying reinforcement learning in order to know when and what stock we have to buy or we have to sell. So basically it is the same problem. The problem of knowing when to buy or when to sell a stock option is the same as ours. And I have seen that recently there is some good papers showing that reinforcement learning can have some excellent results in this use case. So this is why I have chosen RL, because we got some good work on how to know when and how much stocks do we have to buy or do we have to sell. So basically, it's quite the same problem. Yeah.
Please, Maria.
Vedran, can I actually ask you about your, because you're also like obviously leading, efforts in near-term quantum computing and applications and stuff, and you work a lot with, you invited a lot of people from industry. So you want to tell us a little bit about what you think are things that have to happen so we get to what we dream of?
This really feels like you're breaking the fourth wall, right? I'm
just curious.
I'm sharing the panel. Yeah, I think I'm bouncing between two feelings, right? One feeling is that we still need to understand a lot, and that we're running ahead of ourselves in many ways, and that we're doing sort of blind search in something where we should be a lot more systematic, especially when literally billions are at play, like all the time, that could be spent better or worse. And then at the same time, I cannot help not being reminded by the history of deep learning itself, right? And just how much and how large of a gap there's been between the theoretical understanding of what these things can do and what they actually did. And just how much we still don't understand why they work, right? They first worked. Like the Sebenko theorem was not the death of neural networks, even though already a single layer was enough to do everything, right? So somehow, I don't know, I have a feeling that there's room for real experimentation and, hoping to nail down this one thing, which is going to be a miraculous match, and then maybe learning on the level of large case studies, while at the same time we have to push theory, because this might be the only thing that we can rely on in the end, right? But I'm moderately optimistic that something is going to pop up. Moderately optimistic.
And if you're optimistic, then this means a lot.
Oh, well, let's hope I'm not also extremely foolish, which can also be the case. But maybe something that you pointed out in your abstract. In fact, maybe you didn't talk about it that much. That quantum computing so heavily depends on structure, right, and then particular types of structure and so on. But if you step back and think about, for instance, these connections with finance and the problems that Reda is facing, which are machine learning problems. But I mean, these things are modeled with black skulls, which is, essentially the heat equation, and these are ODEs, and quantum computers can do that, right? These become physical systems. And then when somebody tells me, well, I'm approximating this with something which is more general, and now I'm fitting data, then it's no longer, so crazy that maybe something works out, right? But it definitely will be specific.
Yeah.
Something, right? I doubt you'll be able to prove generically that it always works.
Yes, you're very right. So the connection between energy-based models and machine learning, I was talking this week a few times about this, but for example, one of the founders of neural networks, Dunjko, he talks a lot about energy-based models, and they are very complicated neural networks these days, but Boltzmann machines are also energy-based models. And, again, this is a very, if you start thinking about speed ups, it's hard to analyze these models, but if you think about generic links, this is a very beautiful way to try. There's a question. Shall I take this very quickly?
Oh, yes. Let me just read it out. So it's from Alice, just so that everybody hears. So it's that quantum computation has a relationship with the Fourier transform. And do you think that this would show some kind of an advantage in time series processing, which is also actually connected to Reda's question, right? Because it's also time series type problem.
Please try this. This is one of the things I would really like to sit down and study for a year or something. And I think at least this would be a place where you can show where quantum mechanics might help or might not help through the entire theory. Yeah. So please study this and then tell me the result.
So from Pascal's face, I'm realizing that we're slowly running out of time.
Yeah, exactly.
And I think we have just maybe a minute for just one question from Ibrahim, which I think is for either of you. You can decide. It's Amazon uses chaotic inventory management in its hubs. How can quantum computing help with that? Quantum random walk or something like that?
Okay, so it is interesting to see that Amazon is assuming that the inventory is chaotic, because I'm assuming that it is stochastic. Okay, so if for example the quantum computing can help us in a chaotic system, this will resolve the general problem. It will be very interesting to see it, because a chaotic system is very difficult to control. It is harder than a stochastic one. Yeah, okay, so let's see how we can use quantum to handle this chaotic behavior.
Thank you very much. And I think with this, we're now entirely out of time. And I would like to, just before giving the last word to Pascal, Reda, Maria, thank you so much for taking time out of your, I know, insanely busy schedules. It was very much appreciated that you shared your thoughts with us. And you're both, of course, invited to join us in webinars later on. And if you want to pitch into the panel, you're always welcome. So thank you very much.
Well, I have nothing to add, really. Thank you again. Thank you, Vedran. Thank you for organizing this. And thank you to the attendees who stayed up until the end, because I know this is, well, nearly 7 in Paris and Friday evening. So thank you for all your questions. And I hope we will see you again at our next webinars. We're going to have a webinar each Friday during the month of November. And if you're interested, if you want to know more about our program, just go to our website, NISQ.eu. That's very easy to find. Thank you very much.
Bye-bye, good night.
Bye-bye.
Bye-bye, everybody.
Bye-bye. Bye.